This is Bart Kosko from the University of Southern California. This talk will both generalize B-cubed or Bayesian bidirectional backpropagation, and in so doing, introduce a new probability density function that we call Sinc-Squared. You see it on the left in blue. Sinc is the function sine x over x. This function is normalized to turn it into a probability density function when we square it. It's a wavelet-like bell curve with ripple tails that quickly decay. Where those ripples touch the x-axis, you have nodes of zero probability, in contrast to the standard normal density on the right in red, where you have exponentially decaying, monotonically decaying tails. The sinc function, sine x over x, you'll recall, is at the heart of the famous sampling theorem from signal processing that says you can exactly reconstruct a time-varying signal, like the blue signal on left that sums to sinusoids, if you take enough samples and use the sinc function for interpolation. In particular, that function has to be band limited, and the maximum frequency, the Nyquist frequency here, 10 hertz, is such that you have to sample at least twice that. The sampling in this particular reconstruction is at 10 times that, or 100 samples per second. And you see 50 of these uniform samples in the lollipop plot in the center, and the reconstruction, the approximation on the right. The theorem in principle requires countably many samples uniformly spaced, and you put a sinc function on top of each sample. So the reconstruction convolves the sequence of samples with the sinc functions. At the mathematical heart of the sinc function is its compaction property. Its integral over the real line equals just pi, and in a remarkable mathematical coincidence, so too does the integral of Sinc-Squared. Now, since Sinc-Squared is non-negative, normalizing by pi gives a proper probability density function that, again, we simply call Sinc-Squared. Its Fourier transform or characteristic function is just the red triangle you see on the right. Now, this probability has random variables with medians in widths or dispersions, but not variances. Those are technically infinite or undefined, as with the Cauchy distribution, which we'll also look at. In 2 dimensions, the Sinc-Squared looks like a wavelet bell with ripples going off to the side. In another coincidence, if you take the integral over the real line of something with x squared in the denominator and just the number 1 in the numerator, you also get pi. Normalizing by pi, you get back the famous Cauchy density, which resembles the normal bell curve with monotonically decaying tails, but the Cauchy tails are not exponential, they're thicker, they're parallel tails, and so it too has no expectation but a median and either undefined or infinite higher order moments. Bidirectional backpropagation jointly trains a neural network, in particular a classifier, forwards and backwards in terms of the probabilistic structure, the forward probability and the backward. Unidirectional ordinary backpropagation just goes from left to right. And if you do that with a classifier where the input layer consists of identity neurons, as here, for example, an input pattern might be this monarch butterfly on a thistle, and pass that input pattern X from left to right through hidden layers. In our simulations, each hidden layer will consist of 1,000 ReLU neurons, to an output layer consisting of softmax neurons, or an exponential divided by a sum of exponentials that gives back an overall probability distribution of length k, then the probability structure from left to right in the forward direction is just a one-shot multinomial. In other words, it's equivalent to the roll of a k-sided die. Therefore, the negative log likelihood is just the cross entropy. Now, if you train this bidirectionally, you look at the backward probability as well, passing the probability vector, in particular a coding vector like the 1 in k unit bit vector you see on the right, which is coding for the monarch butterfly. You pass that back not through the matrices that encode the weights or synapses, but through their transposes, all the way to the terminal layer, which is now the input layer of identity neurons. And therefore, that's a regressor. That is a type of function approximation. So the bidirectional structure reveals a hidden regressor in the backward direction. And the probability structure of those identity neurons is just a vector normal. Therefore, its negative log likelihood is just squared error. So the joint probability is the product PF and PB. The log of that is the sum. Taking negative logs, we have the sum of the errors, which we want to minimize in the forward direction, cross entropy in the backward direction, squared error. If you take an ordinary unidirectionally trained classifier and run it backwards, you get back visual noise like you see on the left. If you take the bidirectionally trained network, because of the joint training of the two error functions, you get back images on the left at the output as the network tries to reconstruct the image that's stimulating it, given what it knows, given what it has learned and captured in the parameters theta. That will tend to be an estimate of the pattern class centroid, because at the terminal layer, the input layer, again, the error function is squared error. A quick review of classical least squares regression, the Bayesian case. The likelihood is y, given x and beta, the parameters. In the default case, the priors are uniform or flat or uninformative. That's ordinary least squares. If you put a regularizer on the system, that corresponds to putting on a non-uniform prior on the weights. And the traditional approach is to put a vector normal, giving ridge regression or Tikhonov regression. That is a form of L2 optimization, and it gives back coefficients that are non-zero, trading unbiasedness for reduction in variance. If you put Laplacian priors, you get back a form of lasso regression, so-called, that gives sparse representation where a lot of the coefficients are zero. In ridge regression, again, it's an L2 optimization or penalty term being added in terms of the prior. And as a consequence, the constraint sphere is spherical. The yellow hyperplane touches it, and most, if not all, of the coefficients in the estimation are non-zero. In contrast to the L1 sphere that arises in the lasso or Laplacian case, here the L1 sphere is a diamond, a hard diamond, and as a consequence, most of the coefficients are zero, so you get a sparse or compressed representation. We're going to look again at priors put on the weights, and that gives back a proper Bayesian bidirectional backpropagation, or B cube, these regularizers, and this applies locally to the individual synapses here between the layer H1 and H2. So if we take the log prior, in the Sinc-Squared case, it looks like the double sum on the top, in the Cauchy case, the double sum on the bottom, and so forth. If we compare Cauchy on the left in blue with Laplacian, you see something interesting. Both are bell curves, but the Cauchy bell curve and Laplacian bell curve up to scale are transform pairs. In other words, you can show with Cauchy's residue theorem that the characteristic function of the Cauchy probability is just a scaled Laplacian, and conversely, the characteristic function of Laplacian is a Cauchy. It turns out that you can parametrize the Cauchy in effect, in its contours, the diamond structure that you would otherwise get in a hard diamond way on the right with Laplace. So as we change D or dispersion, we get different kinds of diamonds. And we found that that affects the sparsity performance, and the best performance came from the Cauchy curve that had the soft diamond corresponding to dispersion 0.3. Let's just see the second curve in blue. Our two test sets are the two standard image test sets, SciFar 10 on the left, SciFar 100 on the right. The four priors we applied to the B-cube simulations are Gaussian, Laplacian, Cauchy, and Sinc-Squared. In the SciFar 10 case, the best performance we had came from Sinc-Squared. In particular, it outperformed in classification accuracy Gaussian. These outperformed in general uniform or bidirectional, B-squared, and they all outperformed unidirectional backpropagation. But what about the sparsity? How well do these priors zero out the weights, if at all, and still give a good classification? There's no sparsity result in the case of Gaussian and Sinc-Squared, but there is in the case of Laplacian and Cauchy did better. The Cauchy priors, the Cauchy regularizers on the weights in the B-cubed classifier / regression zeroed out about 40% of the weights, whereas the Lasso or Laplacian zeroed out just under 29%. And the best performing Cauchy we found again was a dispersion, the soft diamond D.3 in red in the lower right. In the more difficult case of 100 different types of images, Sinc-Squared again did well, outperforming the Gaussian, and Cauchy did well for the deeper layers, and Cauchy outperformed the Laplacian, both in classification accuracy and crucially in sparsity, now giving Cauchy about 40% zero weights versus Laplace giving just under 23% zero weights. And again, the best performing Cauchy that we found was the soft diamond in red you see in the lower right-hand corner that corresponds to this version of 0.3. The Laplace is on the left. In conclusion, we found that hidden priors improve both classification and regression performance at very little extra cost. And in general, as we found in other cases, that bidirectional performance outperforms unidirectional. The new findings with the new PDF, the Sinc-Squared PDF, in the case of Bayesian bidirectional backpropagation, it outperformed vector normal, needs a lot more experimentation, both in the neural case and more generally in the case of Bayesian regression. And the other finding is that the soft diamond Cauchy performed well and beat the popular Laplacian Lasso for sparseness. So it's a promising alternative for neural classification, again, in general, as well as for Bayesian regression. Thank you.